You are already moving through time right now and cannot stop, slow down, or take a step back. But here is what should thrill you. Not a single physicist on the planet can explain why. It is not that they lack hypotheses, there are brilliant ones, but when it comes to the final answer, every one of them hits a wall. Because time is the most banal and simultaneously the most bizarre thing in our universe. Here is the real scandal. Take any equation of physics, Newton's equations, the equations of quantum mechanics, Maxwell's equations of electromagnetism. Run time backward. Change the sign of the time variable to its opposite. All these equations continue to work. A planet orbiting a star can fly in either direction. Mathematics does not object. Billiard balls that collide and scatter could just as successfully fly toward each other from opposite ends. The laws of physics silently approve. From the perspective of the fundamental equations governing the universe, yesterday and tomorrow are indistinguishable. There is no forward and no backward. There is simply time as another coordinate, like a spatial one. But you wake up in the morning and the coffee in your mug is hot, not cold. A broken egg lies on the floor in pieces rather than assembling itself into a whole. You remember yesterday, but you do not remember tomorrow. Every second of your life, time drives you only forward. Inevitably, inexorably, without the right of appeal. And there is no explanation for this at the level of fundamental physics. None at all. Today we will break everything down from Newton and Boltzmann to quantum mechanics and loop quantum gravity. We will find out why the most brilliant minds of the last 2 centuries could not agree on an answer to a question that each of us asks in childhood. We will get to an idea that makes physicists' heads spin. What if time as such does not exist at all? And to the paradox that Ludwig Boltzmann could not endure to the point that it cost him his life. If this channel interests you, subscribe right now and leave a like, because we have many such breakdowns where we are not afraid to go where science does not yet dare to tread. Do not miss it. Also, follow the link in the description to our Telegram channel. There you will find even more interesting scientific breakdowns. Now, let's go. There is a thought experiment that physicists love. Imagine you are filming a billiard table. The balls roll, collide, and diverge. Now you play the recording backward. What do you see? The balls roll in the other direction, collide, and diverge. And if you showed both versions, the forward and the reversed, to someone who had never seen billiards, they would not be able to say which one is correct. Both look absolutely normal. Both violate no laws of physics. Now film yourself smashing a mug on the floor. Play the recording backward, and the mug will assemble itself from shards, jump up, and end up in your hand. Anyone on the planet will instantly say, this version is backward, because in the real world, mugs do not assemble themselves from shards. Never once in the entire history of humanity has this happened on its own. This is the essence of the problem to which physicists have dedicated almost 200 years. At the level of molecules, everything is reversible. At the level of the mug, it is not. Where does this difference come from? Why does the universe have this categorical no toward the past? Before answering this question, we need to understand how the idea that time is something special appeared at all. Because it was not always like that. There was an era when the smartest people were convinced everything is fine with time, it just flows, and that was that. Isaac Newton was perhaps the most influential physicist in history before Einstein. His mechanics described the movement of planets, the falling of apples, and the trajectories of cannonballs, and did so with such precision that for 2 centuries it never occurred to anyone to doubt his picture of the world. And in this picture, time was something absolute. Newton wrote about absolute, true, and mathematical time, which in itself and by its very nature flows equably and without relation to anything external. Roughly speaking, imagine a giant cosmic metronome that beats time for the entire universe simultaneously. That is what Newtonian time is. It depends on nothing. It does not speed up, it does not slow down, it just goes. But here is what is curious. Even in this coherent picture, Newton could not explain the direction of time. His equations were completely indifferent to which way it moved. If you take the equation of a planet's motion and change the time variable to the opposite, the equation remains true. This is called time reversal symmetry. The Newtonian universe looks the same in the normal direction as in the reverse. Clocks can go both ways. Mathematics does not object. Newton, however, was not particularly worried about this. The direction of time for him was a given, as was its flow. It was something that simply is, requiring no explanation. Philosophers, of course, had been asking questions about the nature of time since the days of Aristotle, who said that time is the measure of motion. But these reflections did not really penetrate physics. Time was the background against which physics played out, not the subject of physics itself. Everything changed in the middle of the 19th century, and the change came from where no one expected, from steam engines. The Industrial Revolution posed a practical question to engineers. How to make a steam engine as efficient as possible? How much work can be extracted from coal? This sounds like a boring engineering task, but to answer it, a new science was needed: thermodynamics. And thermodynamics brought with it something very uncomfortable. It discovered that nature has a preference, or more precisely, a prohibition. The French engineer Sadi Carnot was the first to notice a fundamental limitation. Heat always flows from a hot body to a cold one, but never spontaneously in the opposite direction. This seems obvious. Hot tea cools down. A cold glass warms up while standing in a warm room. But it never happens that a warm room makes a glass even colder while heating itself up. Never. Rudolf Clausius in 1865 formulated this observation into a law and introduced a concept that has since haunted physicists, chemists, philosophers, and simply thinking people. He called it entropy. This word comes from the Greek for turning or transformation, and Clausius chose it intentionally, hinting at irreversibility. His law stated, in a closed system, entropy can only increase or remain constant, but never decrease. What is entropy? Today, the word entropy has a reputation for being something foggy and academic, but in fact, this concept is very concrete. It is a measure of disorder in a system, or more precisely, a measure of how many ways the microscopic components of a system can be organized without changing its overall appearance from the outside. Imagine a deck of cards. If all the cards are arranged strictly by suit and rank, this is a state with very low entropy. Exactly one such configuration exists out of all possible ones. But if you shuffle the deck, the number of variants where the cards look mixed up is huge. Practically any shuffle will give you disorder. Therefore, disorder is not just messy. It is the statistically overwhelming majority of all possible states. This is exactly what the Austrian physicist Ludwig Boltzmann discovered a little later, and this discovery changed everything. In 1872, Boltzmann proposed what is now called statistical mechanics, and with this act, he turned the understanding of physics upside down. He said, "The second law of thermodynamics is not some special mystical law. It is just statistics. Entropy grows because disordered states are incomparably more numerous than ordered ones. When molecules in a system move chaotically, they are with gigantically greater probability going to end up in some disordered state than in a perfectly ordered one." This sounds almost like a revelation. Why do coffee and milk mix if you pour them into one cup? Not because there is some force of mixing, but because the states in which the molecules of coffee and milk are mixed are unimaginably more numerous than those in which they are clearly separated. The system simply wanders through random states and almost certainly always ends up where disorder is higher. It is not a law. It is the mathematics of large numbers. This is how Boltzmann explained why time flows forward. Entropy grows, and this is the arrow of time. The past is a state with lower entropy. the future with higher. Therefore, you know in which direction time flows, toward where there is more disorder. Physicist Arthur Eddington in 1927 called this the arrow of time, a term that stuck forever. But immediately, objections arose. And not just objections, but real intellectual blows from which Boltzmann himself could never fully recover. The first blow was dealt by Joseph Loschmidt, Boltzmann's colleague at the University of Vienna. Loschmidt posed a killer question to Boltzmann. You say that entropy grows because molecules move randomly, and randomness leads with high probability to disorder. Fine. But after all, the laws of the movement of molecules are completely reversible in time. If at some moment we reverse the velocities of all molecules to their opposites, the system will begin to move strictly backward along the same trajectory, entropy will decrease, and the second law of thermodynamics will be violated. How do you explain this? This is called Loschmidt's paradox or the reversibility objection. And it was and remains a serious problem. If every individual process is reversible, where does the overall irreversibility come from? Boltzmann was never able to convincingly resolve this contradiction during his lifetime. He was attacked from all sides. His ideas about the atomic nature of matter were fiercely rejected by a part of the scientific community. Years of confrontation with critics broke him mentally. In 1906, while on vacation with his family in Trieste, Ludwig Boltzmann committed suicide. He was 62 years old. It was a twist of fate. Literally, a few years later, Albert Einstein, analyzing the Brownian motion of particles, provided independent confirmation of the existence of atoms, the very same atoms that no one wanted to believe in during Boltzmann's life. The entire physical program that Boltzmann had defended for decades was correct. But Loschmidt's paradox did not go away. It remains open to this day because it points to a deeper problem. If the laws of physics do not know where the past is and where the future is, then where does the arrow of time come from? Entropy alone does not answer this question completely. It describes the arrow of time, but does not explain why it exists at all. And to get to that why, we need to dig deeper, much deeper, toward the question of why our universe even began in such an amazingly ordered state, because it is exactly here that the real scandal of physics is hidden, and that is where we are headed now. But first, let's truly understand what entropy is in practice, not in textbooks, but in life. Because entropy is not just a word. It is something you feel every day. You just don't call it by its right name. Your room. Clean it perfectly. Put all things in their places, fold the clothes, arrange the books alphabetically. This is a state with very low entropy. There is roughly one way for the room to look exactly like that. Now wait a week, doing nothing. Crumpled clothes will appear on the chair, mugs on different tables, books in random places. Disorder will grow on its own, not because someone specifically scattered everything, but simply because disordered states are incomparably more numerous. Any random interaction with things will increase chaos, not decrease it, because disordered configurations are billions of times more numerous than ordered ones. Now the same with molecules. Before you is a glass of hot tea. The water molecules in hot tea move quickly and collide. The air molecules in the room move more slowly. This separation, fast here, slow there, is an ordered state. For this, a specific organization is needed. But if you just let the molecules move chaotically, they will inevitably mix. The fast ones will share their energy with the slow ones. The tea will cool, the air around it will heat up slightly, and the temperature will equalize. This is the growth of entropy. The system moves from a special ordered state to one that is much easier to realize statistically. It is important to understand one thing. The second law of thermodynamics is not a prohibition by nature. It is a mathematical inevitability. If molecules could move in random directions, and you photographed their state every second, then among millions of these snapshots, the overwhelming majority would show disorder. Snapshots with perfect order would occur extremely rarely. The very word order means something exceptional, requiring special conditions, while disorder means something ordinary, standard, default. This is where Boltzmann made his main breakthrough. He connected the macroscopic concepts of temperature and entropy with the microscopic movement of molecules. Before him, physicists knew that hot tea cools down. After him, they understood why this happens inevitably, and why the reverse process does not just not happen, but is a catastrophically improbable event. Improbable, but not impossible. That is what is important. Boltzmann himself pointed out, the second law of thermodynamics is not an absolute prohibition. It is a statistical law. Theoretically, a fluctuation is possible in which all the molecules in your cooled tea randomly group together so that the tea heats up again. Theoretically. But the probability of this event is so negligible that in the entire time the universe has existed, multiplied by itself a countless number of times, you would not wait for it to happen even once. It is not a prohibition. It is a mathematical taboo. This discovery gave Boltzmann his famous definition of entropy through the number of microstates corresponding to a given macrostate of the system. The more ways you can arrange the molecules so that the system looks roughly the same from the outside, the higher its entropy, and the more that state is a point of attraction for any randomly evolving system. But let's return to Loschmidt's paradox, because it is much deeper than it seems at first. Loschmidt was essentially saying this. Fine. Suppose the system goes from an ordered state to a disordered one because there are more disordered ones. Good. But why does it start in an ordered state at all? After all, if the system were just moving randomly through all possible states, it would with enormous probability already be in a disordered state. Where does the initial ordered state come from which one can grow upward in entropy? This is a question not just about steam engines and tea. It is a question about the entire universe. Why did the universe begin in an incredibly ordered state? Why, immediately after the Big Bang, was everything so dense, so hot, so concentrated, so organized, and why did it give rise to an ordered sequence of events that led to stars, galaxies, planets, and us? If the universe had arisen in a random state, it would with overwhelming probability already be in maximum chaos, thermal equilibrium, where nothing happens and nothing can happen. But it is not like that. It is clearly very ordered by the standards of all possible states. And it is precisely this ordered beginning that gives us our arrow of time. We are moving from low entropy to high, from the moment of the Big Bang to the heat death of the universe in the distant future. The arrow of time, according to Boltzmann, points toward the growth of disorder. We see the past because the past is less disordered than the present. We know what happened before precisely because before means more ordered. Footprints in the snow remain after someone has walked, not before, because the presence of a track is more disordered than untouched snow. Our brain encodes memories of the past, not the future, precisely because the past leaves traces, physical, chemical, neuronal. But the future has not happened yet, and has left no traces. So Boltzmann gave us a powerful tool, entropy as the arrow of time. A system moves to where more states are available. The past is less probable, the future is more probable. Time flows forward because forward for a physical system means toward greater disorder. But this explanation immediately gives birth to a new question. And it is this question that is the central nerve of the entire problem of the arrow of time. If the arrow of time is just the growth of entropy, and if the universe is steadily moving toward disorder, then that means at some point it will reach maximum disorder, a state in which there is nothing left to disorder. A state in which energy is distributed uniformly throughout all space, there are no temperature differences, there are no concentrations of matter, there are no events. This is called the heat death of the universe. and Clausius was the first to voice this bleak idea back in the 19th century. But here, the most exciting part begins, because thermodynamics only describes what happens. It does not explain why the universe ended up in a state of low entropy from which it is now growing upward. It is the same as explaining why a stone falls down by citing gravity, but not explaining who lifted that stone up in the very beginning, who lifted the universe into a state of low entropy, why the Big Bang was exactly like that, perfectly ordered rather than random and chaotic. This is exactly where the physics of the 20th and 21st centuries enters the game. This is where Einstein overturned the very concept of time. This is where quantum mechanics added a completely new layer to the puzzle. And this is where the boldest physicists of our time propose answers that take one's breath away. But first, Einstein, because he did something no one before him dared. He doubted that time is at all what it seems, and his doubt changed physics forever. Newton said, "Time is an absolute background in which events play out, a universal clock for the entire creation." Einstein in 1905 said, "There is no absolute background. Time is not a background. It is part of the physical world, and it can stretch and shrink." Special relativity begins with a simple observation. The speed of light is the same for all observers, regardless of whether they are moving or not. This sounds innocent, but from it follow conclusions that shatter the familiar picture of the world. If the speed of light is the same for everyone, then time for different observers passes differently. A person who moves fast ages more slowly than one who stands still. This is not a metaphor. It is a measurable physical fact confirmed by hundreds of experiments. But general relativity, which Einstein completed in 1915, went even further. Gravity also slows down time. The stronger the gravitational field, the slower the clocks go. Satellites of the Satellite Navigation System are located high above the Earth, where gravity is weaker and their clocks go slightly faster than ours. This is not just a theory. Without a correction for this discrepancy, navigation systems would accumulate an error of several kilometers per day. Every time you use the navigator in your phone, you are using a system that has Einstein's relativistic physics built into it. Now ask yourself, if time can go at different speeds in different points of space, if it is elastic, flexible, stretchable, what does this say about its direction? Why does it still flow only forward? After all, if time can go slower or faster, why can't it turn back? Einstein's equation, like Newton's equation, is symmetrical with respect to time. In the space-time that general relativity describes, the past and the future are mathematically equal. Moreover, in Einstein's concept, a seductive image arises: the block universe. The past, present, and future all exist at once, like different coordinates in space-time. Time does not flow, it just is, just as space just is. Our sensation of the flow of time, the movement from past to future, is something added by our consciousness, not something built into physics. This is a dizzying idea, and it means that the question of why time flows forward and not backward might be asked incorrectly. Perhaps the correct question sounds different. Why do we perceive movement along the time coordinate in one direction and not the other? This is where the paths of physics diverge. Some physicists believe that the directedness of time is an illusion, an artifact of our perception. Others are convinced that it is real and requires a physical explanation. Some look for the answer in thermodynamics and the initial conditions of the universe. Others in quantum mechanics and how measurement is structured. Still others in theories of quantum gravity, where time itself might turn out to be something secondary. But to sort all this out, we first need to find out what happens in the world when we look at it through a quantum magnifying glass, because there, everything is even stranger. In the quantum world, in the world of individual particles and their interactions, the arrow of time is not just a philosophical question, it is a concrete physical problem. and the solution to this problem proposed by quantum physics complicated the picture even more instead of clarifying it. Quantum mechanics describes particles through so-called wave functions. This is a mathematical object that tells where a particle might end up and with what probability. Until the moment of measurement, a particle exists simultaneously in all possible states. This is called superposition. When you measure a particle, its wave function collapses. From all the possibilities, one concrete one is realized. Einstein hated this idea. God does not play dice, he said, but experiments have shown that he does. The equation that describes the evolution of the wave function over time, the Schrödinger equation, is absolutely symmetrical with respect to time. Run it backward, it works the same way. Quantum mechanics at the level of equations does not know the direction of time. This is another brick in the foundation of our mystery. But there is a nuance. When a particle is measured, when the wave function collapses, it is, apparently, an irreversible process. Collapse cannot be reversed. Information about what the state of the particle was before the measurement is lost. It is at this moment that many physicists see the seed of irreversibility, the source of the arrow of time at the quantum level. But not everyone agrees with this interpretation. Some believe that wave function collapse is simply an update of information in our picture of the world, not a real physical event. In the many worlds interpretation of quantum mechanics, no collapse happens at all. Every measurement simply branches the universe into many branches, in each of which one of the possible states was realized. In this interpretation, there is also no fundamental arrow of time. A strange picture emerges. Everywhere you look, in classical mechanics, in electromagnetism, in quantum mechanics, the equations are symmetrical in time. The arrow of time that we feel every second is not built into the fundamental laws of physics. It is not explicitly written anywhere. It arises from somewhere else. And to understand from where, we need to ask the most important question of this entire story. A question that will haunt us until the very end of our conversation. A question to which modern physics honestly answers, we do not know. Why did our universe begin with such an incredibly low entropy? At first glance, this question sounds like an academic puzzle, but in fact, it is the fundamental mystery behind everything you see around you. Behind the fact that the sun shines, that stars exist, that you are sitting now and listening to this, alive, thinking, capable of asking questions. Let's figure out why this is so important. Let's take our thought experiment with the mug and take it to the extreme. If the second law of thermodynamics works and entropy only grows, it means the universe is moving from order to disorder. Now we have stars, red-hot, brightly glowing clumps of matter heating the space around them. This is an incredibly ordered state. All the energy is concentrated in specific points. But in the future, stars will burn out, scatter their heat into space, and the universe will gradually become uniform, dark, and cold. The temperature everywhere will equalize, and nothing interesting will happen anymore. This is heat death. Now think about it. If this is the inevitable future, it means that right now, we are somewhere in the middle of the path from an ordered past to a disordered future. But where did the ordered past come from? Where did the beginning come from? This moment, with incredibly low entropy, from which the journey to chaos began. This is the question that has kept cosmologists in intellectual tension for several decades. There are no answers. There are only hypotheses, bold and elegant. Но ни одна из них не принята всем сообществом, because it is practically impossible to check them. The most common hypothesis is inflation. Immediately after the Big Bang, the universe experienced a period of super-fast expansion. In an insignificantly small time, it increased in size incredibly. This process could have smoothed out all inhomogeneities and explained why the universe as a whole looks uniform. Но инфляция не объясняет, откуда взялась сама эта низкая энтропия начального состояния. It describes the mechanism, but not the cause. Physicist Sean Carroll from Caltech, one of the main popularizers of this topic, is convinced. The mystery of low entropy at the beginning of the universe is a fundamental question about the nature of time, because it is precisely this initial condition that creates our arrow of time. Without it, there would be no past and future, only statistical equilibrium in which there are no processes and no life. Carroll proposes one of the most radical hypotheses. What if the arrow of time in our universe is not the only one? What if the Big Bang gave birth to not one, but two universes? Ours, in which time goes forward in one direction, and a mirror one in which it goes the other way. The inhabitants of each would consider their direction normal because their memories, their cause and effect relationships, and their feelings of before and after are determined specifically by the local growth of entropy. Alan Guth, the creator of the theory of inflation, shares this vision. He and Carroll worked on the idea that from a primary cloud of particles, multiple universes with different directions of time could be born. For us, their time flows backward. For them, vice versa. None of these inhabitants would know of each other's existence or feel anything strange. This is no longer just physics. It is something that changes the very concept of reality. But before moving to such radical ideas, we need to deal with one more classic paradox that for a long time seemed capable of destroying Boltzmann's entire statistical picture. This paradox bears the name Maxwell's demon, and it was thought up by the man who himself laid the foundation of thermodynamics. James Clerk Maxwell, the great Scottish physicist whose equations of electromagnetism predicted the existence of radio waves long before their discovery. But one day he thought up a thought experiment that cast doubt on the second law of thermodynamics and called it very modestly, just a finite being. Imagine a vessel with gas divided into two halves by a partition. In the partition, there is a tiny door. At this door sits a small being, a demon. The demon sees every molecule of gas and knows its speed of movement. When a fast molecule approaches the door from the left, the demon opens the door and lets it through to the right. When a slow molecule approaches from the right, he lets it through to the left. As a result, the right half becomes hotter, the left colder, the temperature difference grows, entropy decreases, the second law is violated, and no work is expended. This paradox haunted physicists for more than 60 years. Maxwell formulated it in 1871. The answer was found only in the 20th century, and the answer turned out to be unexpected. Leo Szilard in 1929 was the first to point out, the demon cannot work for free. To distinguish a fast molecule from a slow one, the demon must obtain information. And obtaining information is a physical process that requires energy and produces entropy. Every time the demon observes a molecule, he inevitably increases the total disorder in the system. But the most precise blow to the demon was dealt by Rolf Landauer in 1961. He discovered the principle that now bears his name. The erasure of information is a physically irreversible process and requires the dissipation of heat. The demon, observing the molecules, accumulates information in his memory, but at some point, the memory overflows, and he is forced to erase it. It is precisely this erasure that is the source of entropy that compensates for the apparent violation of the second law. This result has stunning consequences. It means that information and physical reality are inextricably linked. Information is not something abstract existing in the world of ideas. It is a physical entity obeying thermodynamic laws. When you delete a file from a computer, a negligible but real amount of heat is produced. When neurons in your brain erase old information to record new information, this too is a physical process that increases total entropy. Maxwell's demon was defeated. The second law stood its ground. But this story itself opened up a completely new field, the physics of information, which today is one of the hottest topics in science. And it gave us a new perspective on the arrow of time. Perhaps time is directed toward where the informational complexity of the universe grows. We will briefly move away from the macro world and dive into the subatomic one, where something occurs that does not fit into the familiar picture at all. Because it turns out that although most laws of physics are symmetrical with respect to time, there is one tiny, almost unnoticeable exception. And this exception is potentially one of the keys to understanding our mystery. In the 60s of the last century, physicists studying the decay of special particles, so-called neutral kaons or K-mesons, discovered something unexpected. These particles behaved slightly differently depending on the direction in which the time of their decay was interpreted. This violation is called a violation of mirror symmetry, or, in a more precise expression, a violation of symmetry relative to the combined transformation of charge conjugation and parity. If translated into human language, in the world of subatomic particles, there is a tiny, barely discernible bias. Particles and their antipodes, antiparticles, behave slightly differently. From a theorem that is a cornerstone of quantum field theory, it follows: since one of these symmetries is violated, it means that time symmetry is also violated. The physics describing these particles is not exactly the same when time is reversed. These are tiny violations, one of the few cases in all of physics where fundamental laws explicitly distinguish the past from the future. But how important is this for the arrow of time that we experience in everyday life? Here, opinions diverge. Most physicists believe that this violation is too small and too specific to explain the thermodynamic arrow of time, the growth of entropy that governs our experience. The symmetry violation in K-mesons arises only under certain conditions of the weak nuclear interaction and is in no way connected to why mugs do not assemble from shards. But there is another point of view. If at least one area of physics knows the difference between before and after, it means the universe is not completely indifferent to the direction of time. Perhaps this violation is only the visible part of a deeper asymmetry that has not yet been discovered. Perhaps when we complete the theory of quantum gravity, a theory that will unite the quantum world and the world of gravity, time asymmetry will turn out to be fundamental rather than secondary. Now let's return to what Einstein discovered and look at it once more, only from an unexpected angle, because the relativity of time he described hides something we have not yet discussed. And this something is directly related to the question of whether time is real at all. Einstein, as we have already said, showed that time slows down in a strong gravitational field. Near a black hole, time goes so slowly that an outside observer sees an object falling into the event horizon freeze and never actually get there. For the falling object itself, nothing special happens. It calmly crosses the horizon and moves on. But for an external observer, it looks like a complete stop of time. However, that is not even the strangest part. The strangest part is that in the equations of general relativity, there are mathematically correct solutions in which closed time-like loops are possible. Objects that move along loop-like trajectories in space-time and return to their own past. Mathematics allows them. Physics does not explicitly forbid them. But there is not a single accidental observation that would confirm their existence. Stephen Hawking proclaimed the chronology protection conjecture. Nature somehow always prevents the formation of such loops because they create logical contradictions. But this hypothesis remained just a hypothesis. There is no proof. It is merely an observation that we do not see such loops, passed off as an explanation. This means that from the perspective of general relativity, time behaves like a full-fledged dimension, and there is no internal prohibition on moving in the other direction. All the unidirectionality we observe again returns us to entropy, to the initial conditions of the universe, to that very question Loschmidt posed back in the 19th century. But wait, there is another aspect we have barely touched upon. This is not physics. It is neuroscience. It is how your brain works. And this is where the arrow of time becomes truly personal. Why do you remember yesterday's breakfast, but not tomorrow's? This seems like a trivial question. After all, tomorrow's breakfast has not yet taken place. But this is circular reasoning. Why has it not yet taken place? Because we perceive time as directed. But this perception itself is what needs to be explained. Physicist Richard Muller, in his book, asks exactly this question. How does the subjective feeling of moving forward arise from symmetrical physical laws? His answer is that it is related to how memory works. Memory is a physical trace left by past events. Past events leave traces because they moved the system from a less probable state to a more probable one, and the reverse transition is statistically excluded. We remember the past, not the future, precisely because the past is less entropic and therefore leaves concrete, recognizable traces in our brain. The neurons of the hippocampus, the area of the brain responsible for memory formation, work like a chronometer of events. They record the order in which things happened, creating a neural trace. This trace, a physical change in the connection between neurons, is a record of the past. It is what creates the sensations of before and after. It is the psychological arrow of time. But what is striking is that your subjective time can flow at different speeds. In a moment of danger, when the brain works in hyper-recording mode and captures every detail, time subjectively slows down. During a boring meeting, it speeds up. Under the influence of certain substances, the sensation of time can disappear entirely. People lose the sense of the sequence of events and do not understand what was before and what was after. This tells us something important. The psychological arrow of time we feel is not just a direct reflection of the physical one. It is constructed by our brain based on the information it receives. And this construction process itself is a physical process involving a growth in entropy. It turns out to be a nesting doll. The physical arrow of time creates the conditions under which our brain can form memory. Memory creates the psychological arrow of time. The psychological arrow of time makes us ask questions about the physical arrow of time. And this circle closes on ourselves, on the observers embedded in the very universe they are trying to understand. This leads us to one of the most exciting and controversial ideas in modern physics. An idea proposed by the Italian physicist Carlo Rovelli that overturns everything we thought we knew about time. Rovelli claims, time does not exist. At least, not in the sense in which we are used to thinking about it. In his theory of loop quantum gravity, which Rovelli developed with Lee Smolin and Abhay Ashtekar since the 80s of the last century, space-time is described as a set of discrete quantum cells, atoms of space. At this deepest level of reality, there is no smooth flow of time, no now, no before or after. There are simply states of the system and the relationships between them. The central equation of the theory of quantum gravity, the Wheeler-DeWitt equation, describes the universe as a whole, and it does not contain a time variable at all. The universe, from the perspective of this equation, simply is, like a static object in which there is no movement, no flow, no now. How then does our sensation of time arise? Rovelli answers, it is an emergent phenomenon. Just as temperature arises from the movement of molecules, although no single molecule has a temperature, so time arises from complex interactions between parts of the system, although at the fundamental level there is no time. This means that the arrow of time is not a fundamental feature of reality. It is a statistical effect arising because we are complex systems with memory living in a universe with growing entropy. We perceive time exactly as we do because that is how systems of our type in a universe of our type are constructed. But Rovelli goes even further. He writes, "Heat is nothing more than the movement of molecules. Then why is time not just the movement of things? What if the flow of time is simply what we call the change of states of the universe? What if behind the word time there is no separate substance, only a sequence of events that we interpret as a flow? This is a beautiful idea, but it immediately gives birth to a new question. If there is no time, where does the directedness of these changes come from? Why does the sequence of events always go in one direction and not the other? Rovelli answers, because we are thermal systems observing the world incompletely. We do not see all the details, and it is precisely this incompleteness of our observation that creates the illusion of directed time. This sounds like dodging the answer, but Rovelli insists. This is exactly what is happening. Time is our form of organizing interactions, not an independent characteristic of the world. Not everyone agrees. Lee Smolin, a co-author of Loop Quantum Gravity, categorically does not accept this point of view. He believes that time is absolutely real, that it is one of the most fundamental aspects of reality, and that theories that remove time from equations inevitably lose something important. The present is real, Smolin insists. The past happened. The future is not yet here. And this asymmetry is not an illusion. This dispute between Rovelli and Smolin is not just an academic discussion. These are different answers to the question about the nature of reality. And this question is directly related to why time flows forward. If Rovelli is right, then the question of why time flows forward has no answer in the sense in which we ask it, because time does not exist. There is only a sequence of states, and our arrow of time is an artifact of our incomplete information about the world. If Smolin is right, then the directedness of time is a fundamental fact of reality requiring explanation. And this explanation must be found in physics, perhaps in a theory that has yet to be created. And in the meantime, while physicists continue to argue, the universe does not wait. It continues to grow in entropy, moving away from its unusual initial state, carrying us forward along the arrow of time, where it has always carried us since the first fraction of a second after the Big Bang. Roger Penrose, a mathematician and physicist, the man who proved the singularity theorems together with Stephen Hawking, would not be himself if he simply accepted the standard answer. He approached from afar, with a calculation. He conducted a detailed analysis and got an answer that takes one's breath away. The probability that the universe accidentally turned out to be in such an ordered initial state is described by a number so monstrously small that it is pointless to write it down in digits. Figuratively speaking, if the entire cosmos were filled with fine sand, and on every grain of sand there were another universe, and in each of those universes there was also a similar cosmos with grains of sand, this number would still be incomparably smaller than the one Penrose obtained. Our universe began its journey in a state that, from any point of view, is an absolute exception to all the rules of randomness. And Penrose proposed his answer to this exception, an idea he called conformal cyclic cosmology. Its essence is this: when our universe reaches heat death, when all stars have gone out, all black holes have evaporated via Hawking radiation, and only empty, cold, uniformly distributed space remains, in this final state something unexpected will happen. From a mathematical point of view, this ultimate state of the universe, the state of maximum entropy, will, by its geometric properties, become indistinguishable from a new Big Bang. The universe will forget its scale, and its smooth, infinitely expanded state will seamlessly transition into a new beginning, where entropy will again be low. In other words, the death of one universe is the birth of another, and this happens again and again, without beginning and without end. Each aeon ends in heat death and begins with the Big Bang of the next. If this is so, then the low entropy of our universe at the beginning is explained by the fact that it is not the first. It inherits the geometry of the previous aeon, reprocessed to a state of maximum order through a long cycle of dissipation. The arrow of time in our universe points in the direction that the arrow of the previous aeon pointed, and so it goes in a circle. Penrose went further than theory and stated that he found real observational evidence of this idea in the cosmic microwave background radiation, the echoes of the Big Bang that permeate all space of the universe. Together with the Armenian astrophysicist Vahe Gurzadyan, they discovered concentric circles in maps of the cosmic microwave background, regions with a slightly different temperature arranged in ring structures. In their opinion, these are traces of the merger of supermassive black holes in the previous aeon, gravitational waves that rolled through the end of the last universe and left an imprint on the beginning of ours. The scientific community accepted this idea with caution. Other groups of researchers tried to reproduce Penrose's analysis and obtained contradictory results. Some say, the circles are there. Others say, what Penrose sees is statistical noise. The question remains open, but the very concept that our universe is a link in an infinite chain of universes and that each cycle passes to the next, something like a memory in the form of initial conditions, is one of the grandest ideas ever proposed in science. And it speaks directly about the nature of the arrow of time. Time always flows in one direction because the universe always moves from an ordered beginning to a disordered end. And this end is, every time, the ordered beginning of the next. But there is also a completely different approach to the question of initial conditions, an approach that does not require previous universes and does not appeal to cyclic models. An approach that says, the low entropy of the beginning of the universe is not a problem requiring explanation. It is simply a boundary condition that must be accepted as a given, just as we understand that physical constants have the values they have. This view goes back to the so-called past hypothesis, the idea that the initial low-entropy state of the universe is a fundamental fact as primary as the laws of physics themselves. Why did the universe start with low entropy? Because if it had started otherwise, we would not be here. There would be no one to ask this question. This is the so-called anthropic argument. We observe such a universe because only in such a universe do observers appear. Some physicists find this argument convincing, others consider it an evasion of a real explanation, a way to close an uncomfortable question without answering it. But in the context of the multiverse, the anthropic argument acquires unexpected force. If there are countless universes with different initial conditions, then we would necessarily find ourselves in one of those rare ones in which the initial entropy is low enough for life to arise. This does not explain why the physical laws are what they are. It does not explain why anything exists at all, rather than nothing. But it points to a deep connection between the arrow of time and the very fact of the existence of observers. We are products of the arrow of time. We exist precisely because the universe moves from ordered to chaotic, creating complex structures along the way. Stars, planets, molecules, life, consciousness. Without the arrow of time, there would be no we. There would be no one who could wonder why time flows only forward. This is one of the deepest and simultaneously most disturbing thoughts about the structure of the universe. Our existence is inextricably woven into thermodynamic irreversibility. We are not just observers of the arrow of time, we are its consequence. We are what the universe produces on the path to equilibrium. And while we exist, while the universe has not reached its cold, dark end, one more question remains, perhaps the most radical of all. A question that physicists are only just beginning to consider seriously, and which will require us to completely rethink what we understand by the word time. This radical question sounds like this. What if time is not a dimension of reality at all, but an informational process? What if the arrow of time is not a property of the physical world, but a property of how information spreads within it? It is precisely this idea that, in the very recent years, physicists working at the intersection of quantum informatics and thermodynamics have begun to develop seriously, and the results are already beginning to change familiar concepts. To start with, in December 25, a group of Chinese physicists under the leadership of a researcher named Kai published a paper that made a lot of noise. They proposed a new explanation for the arrow of time, not through entropy in the classical sense, but through the growth of quantum correlations. Their argument is this: in a closed quantum system, as it evolves, correlations between its parts grow. Parts of the system become increasingly entangled in the quantum sense, connected through non-local quantum links. And this growth of correlations is irreversible. To roll it back would mean destroying the quantum entanglement that has accumulated between parts of the system, and this requires such specific intervention that it is practically impossible. The most interesting thing about this idea is this: the Chinese physicists showed that the growth of quantum correlations and the growth of classical entropy are two sides of the same coin. They are inextricably linked, but the quantum version of the arrow of time describes it more fundamentally, not through the behavior of molecules in a gas, but through the deep structure of quantum information in the system. Irreversibility arises here not only because there are more disordered states, but also because quantum correlations grow strictly in one direction. Time flows forward toward where entanglement and correlations between parts of the quantum system grow. And the reverse process of decreasing correlations requires such precise control over every particle that such conditions do not arise in the universe. So far, this is a theoretical work based on idealized models, but it points to the direction in which physics is moving. The answer to the question of why time flows forward lies not in old-fashioned thermodynamics, but in the new quantum informatics. Let's now talk about what happens to time at its most extreme moments, at black holes. Because black holes are not just a convenient example from exotic astrophysics. They are places where the arrow of time behaves completely differently, and where our misunderstanding of its nature becomes especially acute. When matter falls into a black hole, it crosses the event horizon, the boundary beyond which nothing can return, including light. This in itself already sounds like an absolute arrow of time. Once past the horizon, there is no back. Movement is only inward, only toward the center, only toward the singularity. But here is what is strange. Stephen Hawking in 1974 showed that black holes are not absolutely black. They radiate, slowly, negligibly slowly, but they radiate. This is the so-called Hawking radiation, arising from quantum fluctuations near the event horizon. Over an astronomically long time, a black hole evaporates completely. And here arises a puzzle that Hawking himself called the information paradox. When matter falls into a black hole, it carries with it information about its composition, structure, and state. But Hawking radiation at first glance looks like completely random thermal noise without any structure. If a black hole evaporates and all information is lost, this would violate one of the fundamental principles of quantum mechanics, which asserts that information is never destroyed. It can be redistributed, encrypted, or entangled, but not disappear. Hawking at the end of his life admitted that he was wrong in his initial position. Information, apparently, is not lost. It is somehow encoded in the Hawking radiation, albeit in a completely unreadable form. But how exactly this happens, physics cannot yet describe. It is one of the main open problems at the junction of quantum mechanics and general relativity. Why is this important for the arrow of time? Because if information is preserved even during the evaporation of a black hole, it means the evaporation process is, in principle, reversible. Theoretically, this again returns us to the paradox. If everything is reversible at the micro level, where does irreversibility come from at the macro level? And here appears an altogether exotic idea that some physicists call the seed of the real answer. The idea that irreversibility is not a violation of reversibility, but its manifestation under conditions where the system is so complex that practical reversal is impossible, physically impossible. Not because it is forbidden by the laws of nature, but because it requires knowledge and control over an astronomical number of degrees of freedom. Imagine a perfectly stacked deck of cards, 52 cards by suit and rank. This is the reverse state after shuffling. Shuffling is reversible theoretically. One can put the cards back in the required order. But for this, one must know the final state and perform strictly defined movements. Any random movement will only increase disorder. And if there are many shufflers, say 100 and then 1,000, and each makes random movements, the probability of randomly restoring order tends to 0. The universe is a deck not of 52 cards, but of a number of molecules that defies comprehension. With such a number of shuffling, chaotically moving particles, the probability of random order restoration is not just small. It is practically equal to 0 in any reasonable period of time. The second law of thermodynamics is simply a statement of this fact, not a prohibition of nature, but a mathematical inevitability. Now let's move up to another level. We have analyzed thermodynamics, quantum mechanics, relativity theory, quantum gravity. Everywhere, there is the same picture. The arrow of time is not built into the fundamental laws. It arises statistically because of the initial state of the universe. But there is another aspect of this problem that we have barely touched upon, and it concerns the future itself. What will happen when the universe finally reaches thermal equilibrium? What will happen to the arrow of time at the moment of heat death? When the last star has burned out? When the last black hole has evaporated via Hawking radiation? When the last proton has decayed, if that ever happens, the universe will reach a state of maximum entropy. There will no longer be any difference between now and then. There will be no events, no processes, no changes. Does time exist in a state of heat death? This is not a rhetorical question. From a physical point of view, no. Because time, as we understand it, is connected with changes and events. If there are no changes, there is nothing that can be measured as before and after. Time loses meaning. But here is where the truly strange part begins. Ludwig Boltzmann, already in deep crisis under pressure from critics, proposed one of the most ingenious and most disturbing arguments in the history of physics. He said, "Maybe our universe is not a regularity but a fluctuation." Boltzmann reasoned like this. If the universe exists eternally and in an equilibrium state, then sooner or later, random fluctuations will occur in it, small deviations from equilibrium. And the more time there is, the more rare and large-scale fluctuations can occur. Over infinite time, even the most incredible ones. For example, a fluctuation in which several molecules randomly ended up in an ordered state, or several million, or an entire universe. Boltzmann suggested, we live in such a fluctuation. Our universe is a random surge of order in an infinite ocean of equilibrium. The arrow of time exists because we are inside a fluctuation on the path from a randomly arisen order to an inevitable return to chaos. This explanation is terrifying for several reasons. Firstly, it makes our existence a product of pure chance, so improbable that to call it a miracle is an understatement. Secondly, it gives birth to a nightmare paradox that physicists have called the Boltzmann brain. If our universe is a fluctuation, then a small fluctuation is statistically more probable than a large one. It is much more probable that a fluctuation would produce just one isolated brain with a full set of false memories of a non-existent universe than that it would produce our entire vast universe with its billions of galaxies. If you are a Boltzmann brain, then all your memories are an illusion created by a random fluctuation. The entire universe you see around you does not exist. Only you exist for a moment before the fluctuation collapses and you disappear back into equilibrium. Physicists take the Boltzmann brain seriously, not as a real possibility, but as a testing tool. If your theory predicts that Boltzmann brains occur more often than ordinary observers, then something is wrong with the theory. This is called the Boltzmann brain problem, and it is a real stumbling block for many cosmological models, especially those that assume an eternally expanding universe with ongoing quantum fluctuations. Boltzmann, fortunately or unfortunately, did not know about this paradox, but he intuitively felt that something was wrong with his own explanation. His fluctuation hypothesis never became generally accepted. It died with him and was reborn in a new form in the 21st century as a tool for the falsification of cosmological theories. Today's physics has come to a different view on the Boltzmann brain problem. The accelerated expansion of the universe, discovered at the end of the last century, and the existence of dark energy mean that our universe will most likely not reach a state of classical thermal equilibrium. Instead, it will expand forever, becoming increasingly rarefied and cold until it turns into de Sitter space, nearly empty, where only quantum fluctuations of the vacuum remain. In such a space, Boltzmann brains would arise extremely rarely, and normal observers who appeared in a young universe with low entropy would still be much more numerous. This is not a final answer, but it is an example of how thought experiments with extreme scenarios help physicists weed out erroneous theories and move toward correct ones. Now let's come from a completely unexpected side, one that is not usually mentioned in popular explanations of the physics of time, not from a nonsensical conspiracy theory perspective, but from one that individual researchers seriously discuss in academic circles. There is a group of physicists who ask the following question: what if the directionality of time is not a natural feature of physics, but the result of a very specific initial state that was somehow set? Not in a mystical sense, no creator and no magic, but in the sense that the laws of physics we observe might not be the only ones possible. They could be the result of a selection process analogous to Darwinian selection, but at the level of the laws of nature. Lee Smolin primarily develops this idea in his hypothesis of cosmological natural selection. If black holes give birth to new universes, as some theories suggest, then universes with physical constants favorable for the formation of black holes will reproduce faster. Universes where stars do not form and black holes do not arise die out without leaving offspring. As a result of a vast number of generations of universes, the survivors turn out to be those where physics is structured precisely as required for the emergence of stars, planets, and perhaps life. If this mechanism works, then our universe, with its low initial entropy and arrow of time, is neither a coincidence nor an exception, but a logical result of selection. Universes with low initial entropy produce more stars and, consequently, more black holes and more daughter universes. They pass their low initial entropy down to their descendants. The arrow of time propagates through generations of universes as a hereditary trait. This is a fascinating idea. Most mainstream physicists treat it with skepticism because it is currently untestable, but it serves as an example of how thinking about time moves beyond the boundaries of a single universe and begins to consider the entire possible evolution of physical laws as an object of study. Another non-standard angle is looking at time from the position of information theory and complex systems. Stephen Wolfram, the mathematician and scientist who created the Mathematica software system and developed his own view on the foundations of physics, proposes a completely original concept. In his opinion, the universe is a giant computation. The laws of physics are the rules of this computation, and time is the very order of these computational steps. In this picture, the arrow of time is a tautology. Time goes forward because the computation moves in one direction, from the previous step to the next. There is no reverse because the computation does not recalculate its steps. It simply continues moving forward. Critics of Wolfram point out, this is a beautiful metaphor, but not an explanation. It simply reformulates the question of why the computation moves forward and not backward. Wolfram answers, because that is the only way a computation can work. But this answer does not satisfy those who want to know why the laws of physics are the way they are. Nevertheless, the computational view of time yields interesting consequences. If the universe is a computation, then information is primary to matter. Space, time, and particles are all derivatives of informational structures, not the other way around. This echoes Landauer's idea about the physicality of information and research in quantum informatics. Physicist John Wheeler, toward the end of his life, arrived at a similar concept, which he expressed with the phrase, "it from bit." He believed that all physical reality arises from information, and that the act of observation, the act of obtaining information, is a fundamental act generating physical reality. This is an extremely radical view, but it has found resonance in modern quantum informatics research. If Wheeler and Wolfram are right, or even partially right, then the arrow of time is not a property of the physical world, but a property of how information generates the physical world. Time flows forward because information increases in complexity. A computation is always more entangled at the next step than at the previous one, and to turn everything back would mean destroying all accumulated complexity, which means destroying the information itself, contradicting the principle of its conservation. The circle closes again, this time on information. It seems that wherever we look for an answer, we encounter the same structure. Irreversibility arises from the irreversible increase in complexity, whether it is the entropy of molecules, quantum correlations, informational complexity, or computational steps. And this increasing complexity is inextricably linked to the fact that the universe began ordered. But the sharpest question of this entire story remains unanswered. We still do not know why the universe began ordered. We do not know if time is fundamental or derivative. We do not know if it exists at the deepest level of reality, and we do not know if our arrow of time is the only one in everything that is. This is the honest summary of 200 years of work by the most brilliant minds of humanity. Not a defeat, but an acknowledgement of the scale of the question. The question of the nature of time turned out to be so deep that every new discovery does not shorten the distance to the answer but opens new levels of the mystery. And yet we are moving, slowly, sometimes in an erroneous direction, but we are moving. And this very process, accumulating knowledge, building increasingly accurate models, asking increasingly precise questions, is itself an example of the arrow of time in action. Science moves only forward. Knowledge is not forgotten. Every discovery becomes part of the foundation for the next. And ahead of us lies the most important part, the final part of our journey, where all the threads converge, where we will try to answer honestly what we know about time today, what we do not know, and what it means for you and me. Before moving to the final section, let's stop on something very specific, on a question that has been subtly present in our conversation from the beginning, but which we have not given enough attention. This question is, what does it mean to remember the past, and why exactly is this the key to understanding the arrow of time in our own lives? When you remember something from the past, say, last year's summer, you do not see the past directly. You access neural traces, physical changes in the structure of your brain that occurred when you experienced those events. These traces are stored in the form of altered synaptic connections between neurons. They are physical records of past states of the system. But here is what is fundamentally important. These traces store information about the past precisely because the past was a state with lower entropy. Untouched snow can be distinguished from snow with footprints because the footprints are a more complex, less probable configuration. It is the presence of these markers of order in physical systems that allows us to draw conclusions about past states. We can reconstruct the past by traces, by remnants, by records. We cannot reconstruct the future because the future has not left traces yet. This means that our psychological arrow of time, the sensation of moving from past to future, is not primary. It is a derivative of the thermodynamic arrow. We remember the past because the past is less entropic than the present. We do not remember the future because the future is even more entropic than the present and therefore even less specific, less marked. This is precisely why dementia, the destruction of memory, is subjectively perceived as a loss of the directionality of time. People with severe amnesia lose the sense of before and after. They cannot build a linear thread of their existence. Their internal arrow of time disappears along with the disappearance of the traces of the past in their neural networks. This tells us something profound. The arrow of time is not just a physical abstraction. It is what we are. Our identity, our continuity as a person, is a thread of memories stretched from the past into the present. Lose this thread, and the arrow of time ceases to exist for you as a subject. Now let's take the next step and look at how the three arrows of time, thermodynamic, psychological, and cosmological, relate to each other, because their consistency is one of the most striking facts about our universe. The thermodynamic arrow points toward the growth of entropy. The psychological arrow points in the same direction. We remember the past with less entropy, and we expect a future with more. The cosmological arrow, the direction of the expansion of the universe, also points there. The universe expands, and together with expansion, entropy grows. This coincidence of the three arrows is not an accident. It is a consequence of a single cause, the initial state of the universe with low entropy. All three arrows are fed from this source. That is why they point in one direction. If the universe were ever to start contracting, would the arrows reverse? Stephen Hawking once thought so, then revised his position. Most modern physicists believe no. Even if the universe starts to contract, the thermodynamic arrow will not reverse. Entropy will continue to grow. Simply, expansion will be replaced by contraction, but the arrow of time will remain the same. In other words, the arrow of time is not a property of the expansion of the universe itself. It is a property of the fact that the universe emerged from an ordered state. Expansion is merely one of the mechanisms through which this ordered beginning manifests itself in our experience. The picture we have assembled over these hours does not look like a finished mosaic. It looks like a mosaic missing the main central fragment. Every approach explains a part, but none explains the key. Why the universe began with an ordered state at all. This is not a weakness of physics. It is honesty in the face of a question that turned out to be deeper than expected, which means the most interesting part is still ahead. Because any theory that physicists are still building will encounter something we have not yet discussed, the fact that time is experienced from within. And this from within is not an addition to physics. It is its chief witness. And here is the paradox. This very wonder, the ability to ask questions about the nature of time, is one of the most complex products of the arrow of time. Simple systems do not ask questions. Gas in a vessel does not reflect on entropy. A grain of sand does not think about gravity. For a being to arise capable of wondering why the universe moves forward, an incredibly long path had to be traveled from the Big Bang through stars, planets, and billions of years of evolution. This path is the arrow of time in action. Every step of it was a step toward greater disorder and simultaneously a step toward greater complexity. This seems like a contradiction, how growth of chaos leads to the accumulation of complexity. But there is no contradiction. The universe is not an isolated system. Life and consciousness arise in local pockets of order that exist at the expense of the general growth of entropy in the surrounding space. We are ordered structures feeding on the dissipation of heat around us. We are possible precisely because the universe as a whole is moving toward chaos. It is impossible not to appreciate this. Our existence is not a struggle against entropy, as is often said. It is a dance with it. We do not oppose the second law. We are its consequence. Now let's stop briefly and go where one rarely goes in conversations about physics, into the area where serious science intersects with questions that some consider philosophy, others hidden physics, and still others prefer not to touch publicly at all. One of the most uncomfortable questions hovering in academic circles is this: if time is emergent, if it arises from more fundamental structures rather than being initially given, then does it arise the same way for all systems? Here is a concrete scenario discussed in theoretical physics. In loop quantum gravity, time at Planck scales, scales that are more than 30 powers smaller than the size of an atom, is not continuous. It is quantized, measured in separate discrete frames. Between these frames, there is no time in the usual sense. There is only the transition from one state to another. If this is so, then the very concept of between events is an artifact of our scale of observation. At the deepest level of reality, there is no interval. There is only a discrete sequence of states, like frames of a film, between which there is nothing, but which, when viewed quickly, create the illusion of smooth motion. Our time is a movie that the universe is playing. Some physicists go even further. They wonder, if time is discrete, then where does the sensation of a continuous flow come from? The answer proposed by neuroscience coincides with what physics proposes. Our brain does not reproduce reality live. It builds a model based on incoming data, and this model is continuous even when the raw data is discrete. The visual system processes individual snapshots at a frequency of several dozen frames per second and gives us continuous motion. Perhaps our brain does the same with discrete quanta of time, and that smooth flow of second after second that we feel is an interpolation, not a direct observation. This is not just an intellectual game. If the discreteness of time is real, it has consequences for experimental physics. There are attempts to detect the effects of space-time quantization through observations of gamma-ray bursts from distant sources. The logic is this: if space-time consists of discrete cells, then photons with different energies should move through it slightly differently, just as waves of different lengths pass through a medium with a specific structure slightly differently. Photons from explosions that occurred billions of light-years ago should reach us with a tiny delay relative to each other. Gamma-ray detectors are already sensitive enough to look for such delays. So far, they haven't found a hint. Either the effect is too small, or the models of time quantization are not quite correct. The search continues. And here is another aspect that is rarely discussed publicly, but which has a direct bearing on our topic. This is the question of the role of the observer in quantum mechanics and whether consciousness itself is part of the mechanism creating the arrow of time. It sounds mystical, but let's be precise. One of the interpretations of quantum mechanics, the Copenhagen interpretation, asserts that the wave function collapses upon measurement. What is a measurement? It is the interaction of a quantum system with a measuring device. The device is a classical system, but what makes it classical? Some say a large number of particles, others say decoherence, the entanglement of system particles with the environment. Others, including a portion of physicists whom there is no point in naming now because they spoke cautiously and unofficially, cautiously suggest that consciousness is somehow involved in the process of choosing the realized result. This is not a mainstream position. It is a hypothesis located on the periphery of serious physics, but not outside it. Nobel laureate Eugene Wigner asked this question openly. A number of theoretical physicists believe that wave function collapse is a real physical process for which existing theories are insufficient, and that it is in this process that the irreversibility of quantum mechanics is hidden. If collapse is real and irreversible, then every observation, every quantum measurement, is a fundamental act, adding a new irreversible element to the history of the universe. Every click of a detector is the universe choosing one of the possibilities and forever closing the others. And this is the smallest, most atomic act of the arrow of time. That which did not pass through the detector did not become the past. Only what was recorded will enter history. This is a radical view, but it aligns with what experiments show. As long as a quantum system does not interact with other systems, it remains in superposition, outside time in the ordinary sense. Interaction is what imprints an event into reality and makes it part of the irreversible past. Let us continue, because behind all these physical and philosophical arguments lies something strictly practical. The question of the nature of time is not only an academic pastime, it is a question that directly affects how we understand computation, information, the thermodynamics of machines, and ultimately, what the computational future will be. Landauer's principle, that erasing information produces heat, is becoming practically important today. Modern computers are monstrously inefficient from an energy standpoint. Most computing operations are irreversible erasures of information, each of which produces heat. This is one of the reasons why data centers consume so much electricity. Physicists and engineers are working on the concept of reversible computing, architectures in which information is not erased but preserved, which theoretically allows for computation without heat dissipation. This is directly related to Landauer's principle and, through it, to the arrow of time. Reversible computing is an attempt to create processes that do not move forward along the arrow of time in a thermodynamic sense. So far, this works only in theory for simple systems. In real computers, the unthinkable number of interactions inevitably creates entropy, but the direction of research is set. Furthermore, quantum computers, which are now being actively developed, work with fundamentally reversible operations, unitary transformations of quantum states. In a sense, they operate outside the arrow of time until a measurement must be made to obtain a result. At the moment of measurement, irreversibility returns, but the computational process up to that point is quantum and time symmetric. This is not just a curious fact. It points to the fact that the boundary between the reversible quantum world and the irreversible classical world passes through the act of observation, measurement, and interaction with a classical system. And it is this boundary where the arrow of time is born. We are approaching the end of our journey, but before summarizing, there are a few more turns that cannot be missed, because they show how deeply the problem of time is rooted in areas far beyond the scope of classical physics. Let's talk about what happens to the concept of now in Einstein's physics. This seems like a simple question. Now is what is happening at this very moment, right? But in the theory of relativity, everything is quite different. The concept of simultaneity is relative. What is now for one observer is not now for another, moving at a different speed. This is not just a philosophical subtlety. It is a physical fact confirmed by experiments. Imagine two observers. One is standing on a platform, the other is rushing in a train. For the observer on the platform, two events occurring simultaneously at different points on the track are indeed simultaneous. For the observer in the train, one of them happened earlier and the other later. This is not an illusion. It is a real physical discrepancy in what each of them calls now. What does this mean for the arrow of time? If now is relative, then every observer has their own hyperplane of the present, their unique slice of four-dimensional space-time. And the arrow of time for each of them is a movement along their own time axis, which differs at an angle from the time axis of another observer. But the growth of entropy, the thermodynamic arrow, is the same for all observers. Regardless of how you move or what gravity you are in your local frame of reference, entropy will grow. Different observers may disagree on what happened earlier and what happened later for distant events, but none of them sees coffee spontaneously heating up from the surrounding air. The arrow of thermodynamics is invariant. The arrow of simultaneity is not. This distinction is fundamental. It says that the arrow of time we feel, thermodynamic, entropic, is deeper and more fundamental than the concept of now in the theory of relativity. Even if now is different for different observers, the growth of disorder remains a common denominator. Now for something very specific. How ideas about the nature of time can be experimentally verified, and what was already achieved in 1971. Physicist Joseph Haefel and astronomer Richard Keating put 4 atomic clocks on commercial flights and flew around the world twice, in an easterly and a westerly direction. The atomic clocks on the planes ran differently than identical clocks remaining on Earth. The discrepancy was in fractions of billionths of a second, exactly what Einstein's theory of relativity predicted. Time really does flow at different speeds in different gravitational fields and at different speeds of movement. In 2010, a group led by Jun Ye at the NIST laboratory created atomic clocks so precise that they registered a difference in the passage of time when raised by 33 centimeters. Gravity is that much weaker at a height slightly above the surface of a table. Time literally flows faster at your head than at your feet. The difference is tiny, but it is real and measurable. This is not an abstraction. It is physics you can touch. And it tells us, time is part of the physical world, sensitive to matter and motion. It is not an absolute background. It is a flexible fabric from which space-time is woven. But what is important is that with all this flexibility, with the fact that time can go faster or slower, it always and everywhere moves only forward. In weak gravity or strong, at low speed or high, no one has ever observed time reversing locally, speeding up, slowing down, yes, but backward, never. This fact is one of the most reliably confirmed in physics, and yet it remains one of the most unexplained. Let's move on to something rarely discussed in this context, the role of dark energy. We know that the universe is expanding with acceleration, and that this acceleration is caused by dark energy, a mysterious substance that fills space and possesses the property of anti-gravity. Dark energy repels, unlike ordinary matter, which attracts. What does this mean for the arrow of time? Accelerated expansion means that the universe is not just moving toward heat death, it is moving toward it with increasing speed. Galaxies are moving away from each other faster and faster. After a long enough time, unimaginably long, incomparably greater than the current age of the universe, different parts of the universe will be so far from each other that light will no longer have time to travel between them. The observable universe will shrink, even though the universe itself is expanding. Every observer will find themselves in their own small, isolated bubble. This means that the arrow of time for different parts of the universe may, in the distant future, become isolated. Different regions will have their local arrows, in no way connected with others. This is speculative, but it is an interesting consequence of the fact that dark energy does not allow the universe to contract back, and therefore gives the arrow of time no chance to reverse. Another angle is biological. The evolution of life on Earth is a clear illustration of how the arrow of time manifests in living systems. Life does not just follow the arrow of time, it uses it. Plants capture sunlight, high-quality, low-entropy energy, and turn it into complex organic molecules, creating local order at the expense of heat dissipation and low-entropy carbon dioxide. Animals eat plants or each other, continuing the chain. The entire biosphere is a giant machine that maintains local order at the expense of the overall growth of entropy. Furthermore, Darwinian evolution is a directed process, and this directionality is determined by time. Random mutations occur in the past. Selection evaluates them in the present by survival criteria. Offspring carry them into the future. This process is fundamentally unidirectional. There is no backward evolution. Evolution is a biological arrow of time. It moves from less complex to more complex forms, not because it is inevitable from a physical standpoint, but because complexity turns out to be beneficial in a constantly changing environment. We are the product of 4 billion years of this process, and our ability to ask questions about the nature of time is, perhaps, the most complex product of the biological arrow, the crown of a process that itself is possible only thanks to the physical arrow of time. The last turn, and the grandest in its consequences. The many-worlds interpretation of quantum mechanics, proposed by Hugh Everett back in the 50s of the last century. In standard quantum mechanics, until the moment of measurement, a particle exists in a superposition of all possible states. When a measurement is made, one of them is realized, and the rest disappear. But where do they disappear? In Everett's interpretation, nowhere. All possible results are simply realized in different branches of the universe. Every quantum event branches reality. If the many-worlds interpretation is correct, then the universe is constantly splitting. Every fraction of a second, at every point in space, quantum events occur, each creating a new branch. The number of branches grows exponentially. Each branch has its own arrow of time, and all of them move forward. In this picture, the arrow of time is a property of each branch individually, not the universe as a whole. The universe as a whole, including all branches, is a static object, that same block of space-time of which Einstein's interpretation speaks. Only within each separate branch does an arrow exist. And it is in one such branch that you are located, moving forward, remembering the past, and not knowing the future. It is an image simultaneously exciting and disturbing. Somewhere in the countless branches, there are versions of you that made other decisions and experienced other events. But none of these versions can communicate with the others. The branches are completely isolated. Each is convinced it is the only real one, and each is right in its own branch. If this is true, then our arrow of time is the arrow of our branch, a unique, unrepeatable thread stretched through an infinite labyrinth of quantum forks from the ordered Big Bang to some dark, cold future. We do not know if this interpretation is right. The many-worlds picture is mathematically correct, but untestable. That is its most serious weakness. Perhaps it will never be tested. Perhaps it is not science in the usual sense, but something between physics and metaphysics. But it is an honest attempt to answer the question about the nature of reality and what now, before, and after are when the laws of physics are symmetrical, but experience is not. Before reaching the finale, a few thoughts that will perhaps change how you perceive the next few minutes of your life. Every second, about 100 trillion synaptic operations occur in your brain. Each of them is irreversible. Information is encoded and processed, and part of it is erased. And according to Landauer's principle, every erasure dissipates a negligible amount of heat. In total, your brain dissipates about as much thermal power as a dim light bulb, about 20 watts. This is your personal rate of entropy growth. This is the speed at which you personally move along the arrow of time. It sounds prosaic, but now look at it from another side. For these 20 watts, you receive something priceless, a continuous stream of conscious experience, a continuous now, a sense of existence in time rather than outside it. The memories from which your personality is woven, the ability to think about the past and make plans for the future. All this richest subjective life is a thermodynamic process. It is local order created through the dissipation of heat. It is the arrow of time embodied in the neural networks that are processing the words of this script right now. This is exactly what makes the question of the nature of time not just physical, but deeply personal. Because time is not something that happens outside and that we observe. Time is what we are made of. Our existence is existence in time and through time. We do not just move along the arrow of time. We are part of it, its local embodiment, a small wave in the flow that goes from an ordered past to a chaotic future. Now is the time to summarize honestly. 2 centuries of work by the smartest people on the planet have given us this. The growth of entropy describes the arrow of time accurately. Quantum correlations add depth to this. But behind all this stands a question for which there is no answer. Why did the universe begin in such an incredibly ordered state? This is not a failure. It is the horizon toward which physics is moving right now. This is exactly what makes the question of the nature of time not just physical, but deeply personal. Because time is not something that happens outside. Time is what we are made of. Our existence is the universe moving from an ordered beginning to a chaotic end and creating something incredible along the way. A mind capable of wondering at this very movement. We are the children of the arrow of time, its most complex fruits. And the fact that we can ask why, that is perhaps the answer. Not to a question about physics, but to a question about meaning. If this conversation made you think, leave a like and subscribe to the channel. On this channel, we are not afraid of the most complex questions and do not pretend to have answers where there are none. This is exactly how honestly science works, and that is what makes it so exciting.